All right. Thank you for coming back. Like Mark said, I think we kind of know the drill now. The panelists, Rajiv will be from USC presenting first, and then Deshaun from Missouri, and then Connor from Argonne, and Banu also from Missouri. So, yeah.
Thank you. Okay. Hi, everyone. I am Rajiv Mayani. I'm a research engineer at USC, and I'll be presenting KISO. So KISO is a software that we have developed to help users run and reproduce experiments that span the edge, cloud, and testbed environments like Chameleon and Fabric. So with KISO, users would define their experiments declaratively in a YAML file, and then KISO commands can be used to handle the infrastructure complexities. KISO supports different types of experiments, so you can run complex scientific workflows that can spread across multiple test beds or multiple sites of the same test bed, and simpler experiments like single node agentic experiments as well. So typically, researchers without KISO would spend days writing their scripts or notebooks to provision their VMs for their specific use cases, and then installing the softwares by hand or programmatically. And then at the end of the experiments, the results would be scattered across nodes, which they have to fetch back. But with KISO, you would describe all of these in a single YAML file. And then with a single command, you could provision your nodes and set up and configure them. And at the end, all of the results that you have identified of interest to you are brought back to you automatically. And this helps you reliably reproduce experiments on different test beds. So on Chameleon, KISO can provision nodes on Chameleon TAC and the other sites like Chameleon Edge as well. And you could also, within the same experiment, have nodes that are spread across multiple sites and even other test beds like Fabric. Then in the second stage, once the resources are provisioned, we can install a variety of software like Docker, Apptainer, Condor, and Olama. So HT Condor is a distributed workload system like Slurm. And Apptainer is, again, a container runtime similar to Docker, but it's built for high-performance computing environments. And Olama, as many of you would know, it's for hosting open source LLM models. KISO supports primarily two types of experiments, a shell-based, so any bash scripts that you write, you can run with KISO on any of the provision nodes. And the other are complex scientific workflows that are run through Pegasus and HT Condor. And using these two types of experiment, you can run many different edge to cloud experiments of your own. So on the larger flow, KISO takes in a single YAML file, and using that during the different subcommands, it would either provision the resources and configure the software on them. Then it will run the experiments, wait for them to finish, and all of the results that you have identified of interest to you will be brought back to the node from which you have triggered KISO. And then at the end, you can release your resources with a KISO subcommand again. So we'll just walk through a simple Pydantic example. So in this case, we provision a bare metal node on Chameleon TAC, and then we install Olama to serve a 20 billion parameter GPT-OSS model, and then run a Pydantic agent on it. The agent basically simply prompts to the model a question: where were the 2012 Olympics held? And the Pydantic agent harness then translates the response into a Python city location object. So here is the YAML file that you would typically write. So it has three sections in this example. So the infrastructure section, you are defining a sites where you are saying that you want to provision a node on Chameleon for 2 hours of type compute Skylake. And the second section is the software called Olama and the model to pull down, which is the GPT-OSSB. And then finally, the experiment section has two scripts. The first script section installs Python and the Pydantic Python dependencies. And then in the second one, we start the agent and capture its output in the file. And then in the output section at the bottom, we identify the files that you would want to bring back from those remote resources. So to run this experiment, all you would need to do is clone the GitHub repo, have your Chameleon credentials, the application credentials and your SSH key pair set, and install Chameleon with Chameleon dependencies, which is specified as Kiso square brackets Chameleon. And then you would, the typical workflow would have these 4 subcommands where you would have the check experiment command, which checks the Kiso experiment definition for validity. And then you would run the up subcommand to provision resources and install the configured software on them. And then the run subcommand will trigger your experiments, wait for them to finish, and bring back your identified outputs. And then you can release the resources with the down subcommand. So in terms of Chameleon's needs and challenges, the one thing that worked for us was we were trying to write a paper and wanted to reproduce an experiment that we had created a few years back on Chameleon and wanted to try to implement the same with Kiso. And the ability to be backward compatibility helped us in doing that much quickly instead of having to rewrite the experiment again. In terms of challenges, we had some issues with the APIs returning internal server errors, randomly causing failures. And a larger issue that we had were the Chameleon Edge API, which is the only way to interact with the containers, had a timeout that which could not be overwritten. And so when we would run large experiments or large executables or have to download or upload large files or directories, the API would time out and the operation would crash. And a good to have feature for Chameleon has also been mentioned by others, is the ability to connect to the containers directly via SSH or some other mechanism would be really helpful. And I'll quickly go through the more complex version of experiments through Pegasus, which is runs scientific workflows which are directed acyclic graphs and distributed across multiple nodes through a distributed job scheduler like Condors. And setting up such a cluster is very difficult, especially when you try to do it across multiple testbeds or sites, because these nodes could have private IPs, public IPs, and they need to be able to connect to each other. So in this case, we have a 2-site cluster being set up. That's going to run HT Condor. We have one VM that runs as the central manager, which does all of the job scheduling coordination. A second node which submits the jobs or the workflow, and then 2 nodes on the edge which are doing the execution. And then when you do Kiso run, it goes through different stages where it will first copy inputs to all of the distant machines as you have defined. And then at the second step, it will run the workflow and bring back the results at the end. And this is a more detailed flow of the workflow execution. The workflow here, as you see, is represented as a graph. And when the tasks are ready for execution, they get submitted to the job queue where they get spread across the edge nodes when they are ready for execution. And the results are brought back. And for if any of you want to get started on this, we have a starter template kit for Chameleon, Fabric, and Vagrant as well, with Hello World example experiments for both Shell and the scientific workflow version of it. So you can just clone it to get started there. And then finally, we have a website at kiso.scitech.com, scitech.group. And our docs are hosted on Read the Docs, which also has a contact page with Slack, GitHub, and email channels for you guys to reach out if you need help. And that's all I have. Thank you.
Hi, everyone. My name is Deshan Attayam, and I'm from University of Missouri. So my title is Lesson Learned from a Multimodal Question Answering Pipeline on Chameleon Testbeds. So my team is Nagarjuna, Caitlin, and Dr. Tanu Malik. So I'll just dive right in. So this was a project that I did for my semester-long class on end-to-end ML pipeline. So Dr. Malik was our instructor. So we had a team of 3 students, and we had like different sets of pipeline. What we chose was like the text pipeline. The other people choose. We had audio pipelines, video pipelines, things like that to complete. So our challenge was like there's no single LLM consistently yield the best answer across diverse question types, domains or latency constraints. So to investigate how to do a data-centric model routing and dynamically select the optimal model per query. So that was our challenge. And what we built was like we built an end-to-end containerized QA pipeline, embedding based retrieval. Like we experimented with 3 small LLMs. We had 3 routing methods, and we evaluated 30,000 questions. So this was a 16-week course, and we spent like 5 to 6 weeks on these projects. Like we had 3 milestones. The first milestone was actually we did it locally, not on Chameleon. So what we did was like we created a rack-based Q&A pipeline, and it was basic rack method. We generated embeddings, we created answers out of that, and that in there we use some extractive models and different embedding models to see which one performs best. So that was our first milestone. Second milestone, we were instructed to use the Chameleon, and that's where we went into Chameleon. So in there, we started Dockerizing our models, and we created the Minio storage, and we created 3 extractive models. We used 3 extractive models in 3 Docker containers, and we created an initial router, and we had a ChromaDB on Docker. So that was our second milestone in there. So at that point, from that point onwards, we were looking into create reproducible pipelines using Docker and Docker Compose. And then this was the final product of this project. So that's where we looked into Ceph block storage. So we moved into like larger LLM models instead of extractive models. We moved into like 3 different routing modes, which is manual, where you select like, this is my dataset, which model to choose to generate answers. Then we use like dataset based router, and then we used a simple ML based router. So results was not our main concern in this project. The pipeline was. So we put all of our effort in the pipeline, and we used the Chameleon and the Docker environment to create a separate client as well as an evaluator. And we changed our dataset. We used some 3 bigger datasets, which is PubMed QA, Narrative QA, and Hotpot QA. And we used, again, Minio model storage as well. Now the application is end-to-end, and it's reproducible for ourselves because we use Docker Compose. And yeah. And let me tell a little bit about the results. Again, we were not concerned about the results. So on the dataset-based routing, we actually found out that Quen 2.5 did very well for Hotpot QA, and Mistral and Mistral model did well for narrative and PubMed QA, but not that much. On testing performance, we got another 300 questions, randomly selected ones, and just tested out our pre-found the routing method, which data set for which model thing. And again, we got similar performance on Quen 2.5 for Hotpot QA. And that was for the dataset based routing. And for the ML based routing, we started and we used dataset, prompt characters, and context characters as our feature set. And we created a target label using our previously learned data. And what we did was we trained a small regression pipeline to see whether we were able to see like do some dynamic routing on that. We didn't get a good results on the regression pipeline, but as we see, like Hotpot QA actually performed well. Now the performance is a little bit increased from the dataset routing. And then for narrative QA, actually dataset based routing did well. And for PubMed QA, on PubMed QA, actually ML based routing did a little bit bad than the dataset routing, I would say. So now we created the routing approaches, and what we can get from this project is like what we got is like we learned that dataset dependent performance, like no single model dominated. So that means like optimal model selection varied strongly by the dataset type. And ML router that needs a richer features like just the dataset name and the length of the context is not going to make the cut. And from these three routing methods, we dataset aware routing actually wins the game. And also, most importantly, we learned how to build an end-to-end pipeline, like how to configure the networks, how to containerize the environment, like how to create an UI and how to host it through the Chameleon. So we learned all that process from end to end. And what we used was like basically we used like one GPU, like H100 GPU, like with 48 with, virtual GPUs comes with that, I believe, and 250 GB storage, and the block storage, which was an interesting thing because our pipeline kept increasing. Like when we increased the number of number of containers that we have, we needed more storage, so we had to increase it time to time. And we actually used like public port access as well. We had a UI running as well as an API. So that's about the hardware configuration. When I go to challenges and insight, like most of our students, when we get into the milestone 2, we had to create the Chameleon account and start the Trovi notebooks. We had an issue where we had a SSH conflict. Since most of the students weren't familiar with that, we spent a lot of time on it discussing how to figure that out. We finally figured that out when we create a reservation through Trovi. It creates Trovi creates an SSH key actually on the reservation, and that's the main SSH key. You had to manually change it to your SSH key. That's how you get, like, you can access it through Trovi, but you can't access it through your local machine. We figured that out, and we found a workaround, which is the UI. It was fairly easy, I would say, rather than using the other method. UI was very straightforward, and we practiced using the UI for our assignments because we only had like 1.5 week or to 2 weeks for the milestone. We just used the UI that was quickly, we could get it quickly. And I've been working with like 2 other HPCs as well, like Hellbender and Nautilus. So Hellbender is the University of Missouri one, and Nautilus is, I think, it's the National Research Platform. So what I can say is like, in my experience, uh, rather than using Hellbender and Nautilus, it helped us because they allowed like longer reservation times. And since I had 3 members in my team, we had to work collaboratively, and it took like a couple of days for us to go through the code or do some implementation, do these changes. So we needed the reservation for like a longer period. Otherwise, we have to like recreate all our Docker environment, which takes time. And when I talk about storage expansion, we had to do it like on the go. We didn't know that our storage was running out because there's no way to monitor that. Like you can see it for the whole project, but for the thing that I extended, I couldn't find how to monitor that. So that was the problem that we had. And what we wish existed, like some quick start templates that I think that was discussed in the previous call as well, like some pre-built Dockerfile templates or something like that for like Olama, Fast API, things like that, or some straightforward RAG implementations, Trovi notebooks, things like that would be very easy. Like when you create the reservation, if we can get that things downloaded into that reservation, that would make that would save our time. And on the conclusion, to save some time, I'd say I prefer Chameleon or Nautilus and Hellbender. That's my honest opinion. And the full administrative control and longer GPU reservations was my point. And better onboarding templates and AI-aware monitoring would be like significantly improve the experience. And that's it. Thank you.
Thank you, Deshaun. Connor?
Hello, everyone. My name is Connor Bohannon. I'm at Argonne National Lab in the MCS, under the MCS division. And today I'll be talking about building an open source chip prototyping and the PPA evaluation analysis on Chameleon. And then more importantly on what this infrastructure actually looks like and what was required to make this work. The key takeaway today I want to leave you with is bridging the gap between functional RTO and implementing and real implementation is really an infrastructural problem, not just a tooling problem. So before diving into this specific talk, I just wanted to briefly give some context on the broader project. So this is part of the hardware design project on Chameleon, and this focuses on exploring future computing architectures beyond traditional transistor scaling. So broadly, the project looks at open source hardware prototyping, accelerator design, and AI-assisted hardware workflows. So in my case, the focus is building a system that evaluates hardware designs and not just functionality, but physically, looking at things like area, timing, and overall feasibility. So doing this requires integrating fairly large tool chains, from RTL generation all the way through place and route. So if you know anyone or if this aligns with any of your interests, I'd be happy to connect and discuss further. So right now, AI is rapidly lowering the barrier into hardware design. So you can prompt basically any LLM and generate RTL or even higher level code like Chisel very quickly. So the problem here is that most of these designs are only evaluated though at the functional level. So we check if they simulate correctly, but not whether they can actually be built or taped out. So there's a major gap between something that works in simulation and then something that's actually deployable or tape out ready. So bridging this gap requires going beyond simulation to implementation-aware evaluation, looking at things like physical feasibility, PPA, standing for performance, power, and area, and overall design quality. And that's just the real motivation for this work, being able to enable workflows that can evaluate and eventually guide these hardware designs based on real implementation constraints and not just functional correctness. So here we build a pipeline that kind of takes heterogeneous RTO, both handwritten and AI generated, and pushes it through the full physical implementation. The key idea is to move beyond, like I said, simulation and actual measure real PPA analysis and implementation feasibility. Just for a quick example, we can compare something like hardware floating point Unix across multiple open source libraries using metrics like areas and timing and efficiency, which enables evaluation based on what actually matters for deployment, not just whether the design works for functionability. So I believe this is where the infrastructure really becomes essential. So these workflows are not lightweight, and once you move beyond a single run and doing parameter sweeps, you're dealing with batch scheduling, log management, and failure recovery. OpenRoad itself is very CPU and memory intensive, so the cost grows quickly as you scale across designs and configurations. So this is not something you can easily run on your laptop. So what you really need is a controlled, reproducible environment with enough compute power to keep your iteration time reasonable. So, and that is exactly what Chameleon here provides. It enabled us to run these experiments at scale in a consistent and reproducible way. So at a high level, the workflow looks very simple. You generate RTL, you verify, you synthesize it, run place and route and exact the metrics. But the real point is not where we run OpenRoad once. It's the contribution is building a repeatable and evaluation loop. So we take designs, push them through the same flow, and convert the outputs into structured metrics that can be compared consistently. So in practice, you want to make the loops robust and reliable. Was really one of the hardest parts here. And most of the engineering effort here really went into stitching these different tools together in a way that works across these different designs and configurations. Just a quick, so this slide kind of just shows a type of output our workflow can generate. Once RTL is pushed through physical design flow, I don't want to focus too much on designs because that's not what this talk is about. But the key point here is that we can compare designs using actual real physical metrics and not just in simulation. So that just kind of enables things like it actually enables the implementation aware design ranking, which would be a future implementation of this work. moving on to the main part of the talk, a few things that worked really well in Chameleon were, the environment control made the experiments very reproducible, compute and memory, let us treat physical design like an experiment factory. So, we're running large batch sweeps, instead of the one-off runs. And once the workflow was scripted, iteration becomes a lot quicker. So at that point, the bottleneck kind of shifted from actual compute to our tooling integration. So here's just some challenges and remaining gaps that are really more on my end than Chameleon's end. But the infrastructure now exists, but it's not very accessible. So you run into constant frictions, RTL that doesn't synthesize correctly, constraint mismatches, inconsistent units, brittle tooling. So each of these issues, is small on themselves, but as they all stack on top of each other, they can dominate your calendar time. So this is the kind of friction that you don't really see in these papers, but it can determine whether a student trying to reproduce a result, can it be done in a week or does it take them an entire semester? So even when the tool runs, getting it from it works to it's trustworthy still requires the real hardware expertise. So the takeaway here is very simple. It's that capability does not actually equal accessibility. And the key opportunity here is not more CPU. It's just a better workflow design. So, if we want more AI-assisted hardware research, the goal should be, let the researchers focuses on the ideas. You don't want to accidentally become, a flow maintainer for some sort of EDA flow. What would help most with this is pre-built environments. So, snapshots, reproducible flows, simple RTL to metric templates, and better orchestration and experiment tracking. So, just in other words, is we have and need the infrastructure that makes these EDA workflows usable and not just possible. So I'm just going to end it here with the lessons and platform-facing recommendations. So we've shown here today that the implementation-aware evaluation with the open source tools is possible, but the real bottleneck now is the usability. So if we want to scale this, especially for AI-assisted hardware design, we need infrastructure that makes these workflows accessible and not just possible. So this is where platforms like Chameleon, matter and come in. So, I have all my projects down here. If you care to look, the open source for this work is currently still under construction, and then contact info at the bottom. But that's all I have today for my talk.
With SRA fellow Dr. Ashish Gahani and my advisor Dr. Tanumani. So yeah, I think everyone here are using LLM agents and in order to generate the impressive looking projects and for the overall code. And we all use LLMs to generate code nowadays. But in this research, especially we ask like a simple question. We have the generated code and will it pass clean environment test? Or if I take the code generated by the LLM, can I able to rerun it again? And that's what excited us to conduct the research on this. So yeah, let me start with the broader motivation. Reproducibility means getting consistent results using the same data, methods, code, and conditions. And we already have a reproducibility crisis in ML workflows, right? Like where human-generated code itself does not reproduce. So if AI tools generated code that's not reproducible, we believe we are compounding the crisis, but we are not solving it. And this matters tremendously because across scientific computing, software engineering, and AI research, reproducibility is a key factor. So code that cannot be executed by others is not the useful code, as I believe. So yeah, LLM coding agents obviously promise to accelerate software development by generating complete projects, multiple files, configs, with like a simple prompts to millions or thousands of tokens. So here is the scenario. A developer asks for a sentiment analysis app with a prompt, and the agent returns code, manifest file, and the requirements.txt. The implicit promise is that you can just run it and you can able to get the results. But the reality everyone or me found so far is that he can take the code, and when he try to reproduce it blindly, he can't get the same results, and there will be no hidden steps. And when it fails, like what happens is that it's the iterative resolution. You run and you hit an error, you patch something, and you run it again. So we don't know whether the code generated by the AI is from the AI's machine or the trained data, or can it be also running at our machine. So that's what I believe, the environment is as much important as much as the code generation as well. And the gap in current coding benchmarks. So most coding benchmarks right now today evaluate functional correctness. As Dr. Kate and Paul has been also talking in the previous slides about SW bench and site environment bench. So all they care is about the functional correctness, like are the use cases passed or the test cases passed, but they won't see like does the code can get passed on the environment or the mission's environment. So they do not focus, can this project run in a clean environment or the environment that the user might be having, or are the dependencies complete and is execution reproducible using only what the LLM explicitly provided. So does it provide or does it work is meaningless if can it run fails. So we formalize for AI generated projects as executable reliability. So the probability that a generated project runs successfully in a clean environment without any manual fixes. So we use a strict rule over here. It's a success only if it runs in a pristine environment and use the only dependencies that it has listed. And it's a failure if you need any manual debugging, like even 1 minute or missing installs or data dependencies, syntax fixes or path fixes or something such. So here is our evaluation infrastructure. We developed clean and EWS instances, which is Ubuntu 22.04 with only 91 baseline packages, and there will be a complete reset between each of the project. So we evaluate across 3 languages for the agent, Python, JavaScript, and the Java. Same 100 curated prompts sent to all the 3 state-of-the-art agents, which we have used Claude, Gemini, and the Codex, producing 300 projects in total. So we hit the limitations with EC2 and the isolation, and especially the provenance capture. This is where the Chameleon's bare metal infrastructure or the bare metal provisioning would eliminate hidden hypervisor state and give us the full control of what exactly has been loaded on the system. So here are the headline results. Only 68.3% of our overall 300 generated products runs out of the box, and the remaining 31.7% required extensive manual debugging, on average about 15 minutes each. And the primary dependency story is that dependencies required at runtime can be about 13.5 times more than what the LLM has been stated. So we got this by running the 300 AI generated projects, and I will go in detail about each of the results. So to understand the gaps, we use a 3-layer framework. So layer 1 is the claimed dependencies, what the LLMs tell you to install, and layer 2 is working dependencies, what you actually need in order to run the overall project or the overall code. And layer 3 is the runtime dependencies, where everything has been loaded at the runtime, including the transitive dependencies. And reproducibility often fails in these gaps, where reality diverges from what the LLMs has claimed. And this is how we discover working dependencies in practice. We run the project, record success, or we hit an import error, and if there is an import error, we iteratively resolve it. And we cap detect 10 regressions, like we document every failure and fix. And typically, missing dependency cases take around like 2 to 3 iterations. But for the success rate metric, in our evaluation, we made sure that there will be no manual fixes count or no single shot or others as well counted as success. And this mirrors as the real developer experience. Methodologically, we standardize the environment, only Ubuntu 22.04 EC2 instance, exactly 91 baseline packages, and strict reset between each of the project. So there will be no catching between the environments or the projects when we run. And the protocol is install only LLM specified dependencies and attempt execution. And if there is any failure, we document the failure and count success only with 0 manual fixes. And for the transitive capture, we have used Python. Python uses SciUnit runtime tracing, and for the JavaScript, we used NPM dependency tree, and for the Java, we have used Maven dependency tree. So yeah, here are the results. Overall success is 68.3% out of the box, and by the agent, Claude is around 73% because from all of our projects, the Claude can able to run at the zero shot. And for the Gemini, it is 72%, and the Codex, it's 60%. So nearly 1 in 3 projects fail immediately and requires intervention. And each failure costs about 15 minutes or less of debugging time with the agent itself. And also we mark partial cases here, projects that require external services like databases or APIs to be fully functional. Yeah, and LLM treats dependencies as a few lines of text. In reality, dependency forms massive transitive trees. If everyone might here also know like dependency health problem, which is NP hard. Like each of the dependencies, whatever we will be listing, it might get 13.5 times in our evaluation, like where we see like NumPy and it gets like all the transitive dependencies which it might need. So we call this like iceberg effect, where LLM sees the tree and it says like the direct dependencies, but beneath the surface, a Java project asking for 2 libraries might actually load 37. And the risk is simple. Missing any one of these can break the reproducibility. Interestingly, missing dependencies rates are not the dominant failure mode. 87 projects have 0 missing dependencies and only 13% require manual discovery. But overall, only 10.5% of failures are due to missing dependencies. So yeah, we expected missing dependencies to be the main culprit, but dependency problems are to be dominant. Surprisingly, failures are most code generation problems, and version conflicts are around 15.8%. So the insight is LLM struggle with the basic code structure and the robustness more than we expected. So yeah, reproducibility is ecosystem dependent, but whereas in our analysis we found that Python succeeded at 89.2% across all the agents, and JavaScript is around 61.9%, and for the Java it is at 44%. So reproducibility depends heavily on language and tooling, not just on the model. So yeah, this is our surprising result, where we also found agents have undocumented skills, which is hidden specialization by language. This heat map was our surprising finding, where Gemini is perfect at Python but poor at Java, and Claude is the only agent that can reliably handle enterprise Java, and these specializations are not in the marketing materials as well. And these aren't minor differences, they are up to 3x performance gaps. So organizations or anyone who will be using the agents should match agents to their particular tech stack or their particular code. Yeah, and this is where the Chameleon comes in. So the goal one is that we want to migrate all our entire 300 project evaluation to Chameleon bare metal nodes, because unlike EC2, bare metal provisioning eliminates the hypervisor layer entirely, and there will be no hidden state that can persist between runs. So even one project catchy dependencies might not affect the other project dependencies. So that's the reason we want to migrate to the Chameleon bare metal infrastructure. And we currently use SciUnit for Python prevalence capture, but for JavaScript and Java, we relied on package manager's output, which miss dynamic loads. So bare metal access let us extend the system level import looks to all the three languages. And the goal 3 is our pipeline currently takes about 100 hours running serially, because we can't take a single EC2 instance, and we have to make sure to be reset for every single time. And the goal 4 is that finally we want the evaluation infrastructure itself to be reproducible. So Chameleon's snapshotted images and the metadata make this straightforward, unlike the cumbersome of the AWS AMI sharing process. So this is what we have been anticipating, and that's all from my side.
Now I'd like to invite all of the panelists back to answer some questions. So the first question I have, well, first, thank you, presenters. I think a lot of interesting use cases across Chameleon, kind of diverse use cases from chip design, LLMs, and workflows on Chameleon. So one common thing that I'm curious about for all of you is when you go to a testbed like Chameleon and you're looking for resources, how do you find those resources? How do you find what hardware to use and decide what hardware to use? And I would take that even further, not just the hardware, but also any services that the testbed provides, like heat or things like that, or images, right? So different images. So if there's other people in your area, maybe in chip design, and they've shared images, how would you go about finding those? So I'm curious for all of you, how do you find those kinds of things on a testbed?
So for us on the scientific workflow side, it's mostly we are running someone else's code, so it depends on what their codes requires, whether the architecture, the memory requirements, and things like that, and what all of the other also depends on the user's applications that they are trying to run through the workflows.
So when you go to a test bed, yeah, oh, sorry, continue.
Yeah, so that's where so it's usually just what code we are trying to run that comes from the user, and we just are making it easier to run it on a distributed cluster. So our scope is much more limited. It depends on the user applications.
But you still have to map those requirements to the test bed. So how do
Yes,
you
it's
connect
for
those
us,
dots?
that's where we are the architecture, it's AMD ARM64, the amounts of RAM required, and that's how we identify the resources to provision. As I was saying, then if you want to spread it across multiple sites, then the networking setup, whether can we get floating IPs on demand and so on. So it's simpler side of things.
Okay.
Yeah, in our case, we usually see what is our compute that we need in order to see how we can run the programs or the projects on the machines. So it depends mainly on the scale that we are currently running. Let's say if you are running the 300 projects as I mentioned, then A100 would be more sufficient for us. So it's like a direct answer for us. A100 is the one that we needed. So that's what we will be requesting from the Chameleon. But for this particular project, the reason for using the bare metal infrastructure is what I have been kept on saying, because for each of the project we don't want the other project cache dependencies to be on this. So for this reason, the bare metal infrastructure is what we need more, and that's all from our side. So it's like regarding your question, it's like a straightforward where we know what's the scale, so what's the GPU that might be needed for that. All we need is the bare metal infrastructure in order to run them. So.
Okay. Connor?
So it's an interesting question on my end because as far as I'm concerned, there's no one on Chameleon or most cloud servers doing open source chip design, only because a lot of times when you get to a design that you are ready to tape out, you usually go and try to get some sort of industry PDK to be able to tape out, because a lot of these open source ones, they're still just estimations. But that was another thing in my work is I want to try to bridge this for research purposes into Chameleon, and I think I'm going to make a blog post soon with my work and everything and talk about this, because like a lot of times is, we use these open source tools to get an idea of what the end ASIC or tape out chip is going to look like. And I think this is even better for like students that are trying to get into this open source chip design thing, because when it really comes down to it, you have your companies like Cadence or Synopsys. I don't know if anyone's familiar with these companies, but they run, and then you have like Taiwan making taking out all the chips and everything. So you have it's very industry led. There's not a lot of open source, and the reason about why it's not a lot of open source is because these Cadence and Synopsys, they're American industries, so they don't want to make their stuff open source, and then chip design becomes prevalent in other countries, because that's a big economy boost in the U.S. right now, right? So, but I think it'd be interesting to make more images or snapshots on Chameleon for people to get into this open source kind of chip design verification. So that's why I'm working on this framework and everything.
So Connor, actually, I was going to ask you a question. It sounded based on the presentation you gave, it sounded almost like you would be interested in building a platform on top of Chameleon that would support that chip design. Because earlier on we had this conversation about how we can't really support, all the images that everybody would ever want to have. We can only support a very small number of images because each image requires effort to maintain and things like that. And there are other reasons, which is that some types of configuration or platform style stuff, we just simply don't have the expertise to support, right? So MPI, for example, we're not distributed computing people, we can't support that well. and you seem to be well positioned to support those types of things, right?
Yeah, that's the problem. There's not a lot of people, because I think in this realm of this chip design is, a lot of people go to industry because, you can make so much, a crazy amount of money. So a lot of people, they don't stay with the open source, but with OpenRoad, it's maintained now by UC Berkeley pretty well. So a lot more people I see are using it. So yeah, I think it could be interesting. I think there's a larger push with the AI assisted chip design stuff because of the Genesis mission, with stuff like that. So I'm working on this framework and I only worked on it for a couple months, but I mean, yeah, I think I could be interested to build a platform on top of Chameleon or just anything that, help people either get into the chip designing world or help people bridge because, a lot of people, I think a lot of people aren't in the hardware world.
Yeah.
So anything to make it easier, because like right now, like with LLMs when they first came out, made it easier. Anyone can just, type in, generate a code and, have it do something. So I think it'd be interesting to, try to bridge a gap and, try to be like, well, I want to create this,
So this-
application-specific chip, and then you can
This,
do
this
it.
could actually be positioned multiple ways, right? One is build a platform on Chameleon, and then the other one is perhaps work with the folks in Berkeley to build a different packaging of the open source platform they provide, right? And the different packaging is effectively, like Chameleon snapshot of something, right? Just gets updated or a workflow to build that snapshot. But a follow-up question on this is, does Chameleon have the architectures that are, in terms of hardware, do we have everything you'd wish for to support this kind of work?
I think Chameleon maybe lacks like certain FPGAs I would like to have. Maybe like if you could look in like the V80. I know they're very expensive FPGA cards. They're like $10,000 each or something. But there's certain FPGAs that I think could be useful.
Did you say 10,000?
Yeah, they're about $10,000.
H100 nodes are 100,000.
Oh, okay, that's good. But yeah, like being able to have like a cluster of V80s or something could be very useful.
How many is a good number?
We have 2 at Argonne and it works for me so far.
Yeah.
But I don't know, maybe like we haven't got into that part of running large batches and stuff, but I mean,
Yeah.
I think,
So,
anything is like.
this is where the benefits of having a community around a certain research question, a set of research questions like, what you're talking about, hardware design, is very useful because if we see a community, we can actually build out decent hardware capabilities, right? I'm kind of thinking that FPGAs right now might be easier to buy than GPUs.
Yeah.
As far as that is concerned, right, that would be a place where we could move in immediately, right? But the question is, you saw that saturation or the popularity context kind of graph that I showed, right?
Yeah.
If we buy something and it's in the sort of 20% usage or 10% usage kind of space, right? We're not going to buy a lot of it, right? And if we buy something and it's 100% usage space, doesn't matter how much it costs, it's a bargain, right?
Right.
And I just want to give Deshaun a chance to answer that question, and then, we can move on to.
Yeah.
So my case was like different from these guys. So it was a 16-week rapid course. So I didn't had like much time to do some experiments, find the best resource I need. So what we did was, as a team, we found that H100 with our LLMs, it worked better. And we found the OS image, and we found out that, okay, using GUI actually make it easier for us to do the reservation and to kickstart things, and we just stick to it. All throughout all the projects, whoever made the reservation did the same thing. We followed that, we documented that step. That's it. Thanks.
Freddie, I think you.
Yeah, I have a question for Manu. So can you clarify, you're saying you need to use bare metal on Chameleon because of cached state, but you're doing stuff in software, right? So when you bring up a VM, you get a fresh copy of the OS. What exactly is the cached state you're concerned about?
So let's say I will come with an example. Let's say I have the artifact A1 and I'm running it on a machine on OS Ubuntu 0.02. And when I'm running A1, and I got like few of the dependencies. And when I have installed and executed them, I got the translated dependencies. And when I running like after the build complete and when I executed, I also got the runtime dependencies. And now I want to run A2 over here, which is the artifact 2 on the same machine on the same GPU. The problem here is
Aren't you like relaunching an instance in between?
yeah, exactly.
Like, I'm not sure what the benefit of bare metal versus VM is.
Sorry, I didn't get your question. Can you repeat it?
I'm not sure what the benefit of bare metal versus VM. I understand in any case.
No. The reason behind why I'm saying about the bare metal is that the other artifact, when I run, the other dependencies that I already have in the A1 won't be affecting on the A2.
Yeah, it sounds like you. Hypervisor, that's.
No. I was saying like whatever the transitive dependencies that are already loaded on the machine
Uh-huh.
will be affecting the other artifact is what I mean.
So whether you're using bare metal or a VM instance, right? If you want a fresh slate, you launch a new instance to evaluate to do a new artifact.
And we also plan of extending this work at the GPU level as well, like in order to see like how well these are working on, let's say the Valor, whoever has presented the self-iterative loop or the self-correcting loop, where they have tried to see the power efficiency of running the program, which is like pretty similar to our
So let
work.
the agent self-correct.
Exactly. So that's where the bare metal will be also helping us. So that's what we thought of extending the work to the bare metal infrastructure.
So if you do this on a VM, like I don't think there was anything cached on the VM if you're launching a new instance every time, and it's going to be like 30 times faster to launch an instance.
Yeah, in order to parallelize the work, we also thought of bare metal infrastructure, and the Chameleon would be a great option because we can parallelize all the 300 projects at a time instead of we running every single time and resetting each of the project.
Can't you do that on VM instances?
Yeah, we can do, but the cost will be like very high when it compares with these particular.
VMs at Chameleon.
Yeah. So we're talking about like instead of using bare metal Chameleon sites, use a VM site on Chameleon. It's a similar type of workflow, right? You'll still like launch a new instance for each experiment, but it's approximately 30 times faster to launch an instance.
Yeah, we will plan of using them. We haven't exploded on the Chameleon, and all the evaluation that we have done is so far is on EC2. So that's the reason we plan of extending the work so that we can also see the other aspects like how we can get the benefit of the power efficiency as the other presenter who has presented, and also see the like where this project can lead us across all these advantages that we have from bare metal infrastructure and also from the VMs as you have just mentioned.
I actually had another question. So since the whole goal here is reproducibility, have you considered running this using self-hosted models, like open weight models, so that you can get some reproducible results and you won't have to concern yourself with model deprecation?
No, we haven't run any self-hosted models on over here, but there is one more project that we have been working on, which is self-hosting all these LLMs, and it's same as the Dr. Pion's work, like multi-objective optimization in order to efficiently run all the self-hosted models. So that's where I think this might be like more helpful, and where we need like the better GPU infrastructure, because we have hosted like let's say 2 billion parameters to 60 billion parameter models, or let's say DeepSeek 785 billion parameter model as well on the persistent VM, and we can't run like the 785 billion parameter model on a single GPU, or even if we say H100s like Dr. Kate has been saying, we can't run like 785 billion parameter model on a single GPU, and that's where we need like 2 or 3 of the H100s, and our goal.
4 GPU instance.
Exactly, yeah. So that's where this particular problem has arisen, and that's what I thought of talking about when Dr. Paul has been saying about like what is the compute requirements that you might be needed. I thought of that's what I thought of responding back after him.
So I think this brings up maybe a more general question about kind of LLMs and these models on Chameleon. You're all using them in some form. What do you feel like is missing more generally for a test bed? Because it seems like, I'm hearing a lot today, like a lot of people are doing a lot of the same things. So is Chameleon lacking something that would make your work easier in this space?
I would say the better evaluation metrics would be helpful, like monitoring what's the resources for each of the query that we will be running. If I take an example, we are like instead of we self-hosting the large language models on the GPUs, like if Chameleon can automatically run all those models with the persistent volume, and like if each of the user can see like each of the evaluation metric, like what's the GPU utilization. It's not like in the shared GPU infrastructure. What's the problem is that we can't see my evaluation would be different other than his evaluation or the other people who will be evaluating. So we can't see like each individual metric that we want to see, like let's say cost, let's say latency, because all the GPUs are running by some other else, and we can't see like each individual user. So that's where I think this might be very helpful.
Okay, how about, I mean, this is a question for the panel, so do other people have ideas for what is maybe missing, on Chameleon?
Maybe you guys could find out how many people are running these models and whether it makes sense for you to host them
Okay,
and have like a quota-based or token-based approach for the users.
So quick follow-up question on this. So we actually considered this, but I don't know, relative to large, domain science production resources, we don't have that many GPUs, right? So any models that we would host would take away from the bare metal or configurable GPUs. What would you rather have?
I mean, it depends on your use cases, right? Like what your users are actually
Yeah,
using.
but
Well,
I'm
for you
asking
guys,
you,
so,
right?
yeah,
Yes. For me, I personally I'm on the computer science side, not the science side, so I'm taking other people's code and translating into workflows. So I don't personally know, what's the requirements depends on the science researcher's
Yeah,
code.
but I'm just a random poll, right? As it were, what would you guys prefer from the perspective of your use case? More bare metal GPUs or models?
What models would they be?
Propose something,
Well, I mean, are you restricted to open weight models?
yes.
Yeah,
None
that's a
of these
good,
guys are
that's
using
an important clarification.
I guess you could just start off with one node and have tokens granted out and see how much the utilization is, and based on that, build
There are
it
already
up
some
more.
like very inexpensive providers for open weight models. So if you're restricting yourself to open weight models,
Yeah.
not clear.
I may also be biased here because I'm given like all
We're leaning to
models
bare
through
metal
our
then?
so.
I mean, I'm benchmarking against Open Router, so, that's the thing, is that's turned into like an industry. And now you'd be competing against an industry in that sense.
Yeah,
And there are tons of like providers that are basically subsidizing these open weight models and serving them way under cost and collecting data from it and all that, so hard to beat that.
It would be efficient though, wouldn't it, to just like, these are the models I'm working with, throw them in a persistent store and then just fire them up as you needed them, like,
You can do that already.
yeah, I mean, that seems like, that might be, like, maybe having a best practice for people who want to run lots of these, but like load it up and tear it down.
yeah.
For
Okay,
students,
so-
I
That
believe,
could be an alternative.
yeah, for students, I believe they would prefer more models, something at least. From my experience, I know that Nautilus has hosted a couple of models. They do have, we can request like this number of tokens or this number of compute time. They already have hosted a couple of months. I don't know which of them, like
Yes, they hosted like all the open source models that they have, like the famous ones. Let's say they have like a family of Lemma 30 billion, and they haven't deployed the Gemma or some other model of the same parameters. Instead, they deployed Gemma 200 billion or Gemma 6 billion, like different parameter sizes and across different models. That's what they have developed. And yeah, it's a very interesting aspect because many of the HPC conferences or ISC people, all these people are mainly concentrated on how many, like the GPU utilization, because the enterprise won't be giving us this info, like the OpenAI or the Claude or let's say Gemini, they won't release any of these metrics. But if Chameleon or Nautilus or any infrastructure like this would also release this type of data, then that can help other people who will be researching on that to try efficient models or to fine tune the efficient models, and also see the GPU aspect or the utilization aspect of each of the individual queries or something such.
My point is like, we had like 20 students in the class, so each of them had to run at least one LLM model on Chameleon. And that doesn't make sense.
Yeah.
But that was part of the class, right?
That was part of the class.
So we're supposed to be having the experience of deploying it, not
So
using
that's
it.
an exercise.
right, so that seems like kind of an argument for
keeping the bare metal.
Right, to not take those machines and make them general purpose, model serving for everybody, that you don't have to set it up, right? If you keep the bare metal or, the VM access to the nodes, then students can learn how to do these things themselves, which kind of leads to another question I have in terms of, is there anything about, especially in this space with AI on Chameleon and, the GPU nodes, for students that you found is too difficult? So we hit on one, I think, Trovy, some frustrations there. Is there anything else that was kind of too fragile or, slowed down a class where the students spent too much time dealing with Chameleon instead of doing their assignment?
From me, I think I was the one who brought that issue. So apart from that, I think everything else was smooth. So we needed to see how our storage grows at some point. Like when we stepped into the milestone 1, and when we stepped from milestone 1 to milestone 2, basically we had more Docker containers, we had larger models, so our storage grows. So we had to do it dynamically, like on the run, we had to increase our storage and run back the compose again. So Chameleon supported that very well, so we were happy about that. I didn't have to none of us had to restart the reservation and get the storage in, just like the other, comparing these to other HPC. So that was fun and that was interesting. Apart from the Trovy issue, when we figured that out, it was all smooth right for us.
So that issue seems like a bug because there's supposed to be like a startup script on the Chameleon-based images that should load all the keys in the profile. So if only the Trovy key was loaded, that means that script either didn't run or failed when it ran. But that's actually not something you have to work around, it's something you should have filed and helped us to get it out. But since that's like a very undocumented feature,
Yeah.
I don't think people know that it's supposed to.
I think this is either that it's something that's supposed to work, or Python Chi makes assumptions about the easiest way to use Chameleon, and it sounds like that.
But
might-
assuming
might
they're
have
using
not.
the base image, the CC load
But
key should have
yeah,
run.
yeah.
Investigate and document.
We've had
Did you
issues
file
where
a
like
ticket
it
for
didn't run if, let's say, there was a key in your profile that has like a non-ASCII character comment or something like that, it makes it not run. So it could be something like that and you just didn't
So the
realize it was
students,
supposed to
like,
happen.
They usually don't report bugs. What they do is we had a discussion board, but someone put in the question, we had a discussion, someone found the answer, okay, use UI to figure that out. And then we were all using UI and that's it.
Well, that works. All right, other questions? Yeah, Cody.
Connor, you mentioned that you would like to have seen more workflow management for your long-running stuff. What would that look like for you?
But that's more, I think, on the future implementations on my end, for my workflow, but having maybe, because right now what I have with the AI is I either have handwritten or generated RTO code, and then I run it through something, either Yosis or CocoaTB, and these are just kind of test benches, or Verilator that can do like accurate simulation or count the cycles, or with Yosis, it does actual synthesis, so it gets code ready to then run it into OpenRoad to do place and route, get timing, get performance, get power, get area estimations for actual tape out. So what I do now is, I either generate these codes in Chisel, which is a high level synthesis of Verilog or system Verilog code, and then I run it through these test benches, and then this you have like your SBT and you run your test, and then if it passes or fails, if it fails, then I send back to some context pool, and then I regenerate it or change it. Very similar, but for the gap in between actual simulation and tape out, you have different metrics you can change. You have like area utilization, you have your timing, you have your max frequency on what you want to run the chip. And there's a lot of different things that you have in the actual hardware design. So being able to, I don't want to train my own model because, that wouldn't make any sense and that'd be too much, it costs too much money probably to even try to do that. But use some existing LLM that can, take a lot of these, config scripts in OpenRoad and then, run a bunch of different setup parameters and then see which ones fail, which ones pass. Run that through some sort of context pool and then regenerate that RTO.
So this
code.
wasn't something about operating Chameleon in a...
No.
Okay.
I think probably for this, it's my workflow, but I mean, like, I think Chameleon works really well for what I have. Honestly, I'm probably like underutilizing Chameleon in a way. I feel like it could be better, but yet again, like I was saying earlier, no one in my realm of work really uses these cloud servers to do this kind of stuff, right? Because, I mean, a lot of with these industry PDKs and stuff, it's easier to just, once you have a design ready, and you run it through these simulations, but once you have a design ready, you kind of ship it off to industry and try to get them to tape it out for you and everything, right? So.
Thanks.
Other questions?
Just because orchestration has come up a lot, and people are talking about moving things between clouds, I wanted to highlight that Chameleon does support standard OpenStack APIs and Terraform and Ansible using those APIs. In terms of that, the only sort of customized part is making a reservation, but we have examples where you can make a reservation and then throw Terraform at it, throw Ansible at it, throw any sort of existing tool that knows about OpenStack or has an OpenStack plugin at it. And so you might find that useful if you need to automate hundreds of VMs or automate some workflow thing, or you could build an orchestrator on top of this, leveraging that.
Other questions? And I've got more too.
Yeah, I had a question about the routing project. So what did you think was gonna be difficult when you started, and when you finished, what was difficult that you hadn't expected?
So, first of all, what we think that was going to be difficult was to host the LLMs. Because we haven't taught, none of us in our team had hosted 3 LLMs together and had tried out dynamic routing. But in the end, that was the easiest thing to do. Because none of the other platforms allows you to install, Hellbender doesn't allow you to install Olama itself. Nautilus does, but there's a cap on 6 hours or something like that. And then they just destroy your Jupyter mod, something like that. So while using this, it was very easy to, we used Olama, we just installed it, we just had the container inside. That was the easiest thing to do. Hardest thing was to manage the storage. Initially we thought, okay, that just request 50 GBs or 60 and then do our work and that's it. But we suddenly started getting errors stayed in that, okay, you don't have enough space because you have multiple containers running in. So we had to go back and think, okay, are we installing dependencies that is not required? Yes, we were. So we had to remove them, increase the storage, and we had to optimize that like that.
Were you using the on-the-node storage, or were you using object store? Or?
We were using our own containers, we built our own containers.
Those are Docker KVM?
Yep.
Okay.
Oh, VM, okay.
So you filled up the root disk and had to.
Exactly.
Okay.
We filled up the root
Because the
disk.
default size is way too small.
So, and you
Yes.
didn't think to use Cinder or volume storage with VMs?
Initially, no.
Okay,
But-
but eventually?
Eventually, what we did was when we had a question, we went into Trolley and typed that. We have this issue, how to increase the storage on your VM. Trolley had notebooks for everything. So that was a plus.
Can you tell me more about these notebooks? Which ones?
Trolley had
Are you
artifacts.
talking about
Yeah, Trolley artifacts,
examples?
exactly. So it
you
had
literally
Like
typed
references
that
for-
question into the Trolley search box?
just the keywords,
And-
how to increase the storage in here. Trolley gave us an artifact.
Read the chatbot interface.
Well, so yeah, we
Yes,
recently improved the search on Trovy, so I'm glad because I don't think that would have worked before.
Is it full text on the description there?
Yeah, it should be authors, descriptions, all that, which I think is what would allow you to pick
Well,
that
this is
up.
amazing.
Yeah.
Yeah, what was it
I'll
for?
say,
I'm gonna check.
we have a blog, we probably have a blog titled How to Increase Storage.
I know, agree.
It's hard to find.
But these
I know.
students are taking 4 classes per semester and doing so many other
Yeah,
things. That's it. They don't read blogs. They just so it's
I just put increased storage into the Trovy search query and I got no artifacts found.
Okay.
oh
Have to
I guess you
refine
got
your
lucky.
queries.
I guess
Maybe
Um,
they put something else.
something else. I can't remember the exact keyword.
So I've got a actually related to all of this. Question for the whole panel again. When you go to a test bed, how much time do you say you spend learning kind of the test bed and trying to find these things, how to do it on the test bed as opposed to doing the work you want to do? And then with that, what resources, in particular on Chameleon with documentation or Trovy artifacts, would be helpful? to make this experience better. So just kind of to take what you're talking about, make it a little more general and for the whole panel here.
So at the start, we had to put like a little bit of time because we were not familiar with it. And then when we figure out, okay, this is what we had to do, it was very easy. Like,
Well, how did you figure that out? Trial and error?
so trial and error, that was the
Okay.
method. Yeah.
Okay.
We didn't read any of the blogs or any of the support notebooks. So.
Connor, yeah.
I was talking with Mark earlier about this, but at least for my setup, it's very simple and straightforward. I mean, I was just using like a Compute Skylake node or whatever, so very easy. But as I was telling Mark, is that the actual getting started ready or the docs, they haven't been updated in probably the past 6 months, I think, of when I've started using Chameleon. So like they still, and like the getting started docs, you know, the setup is like, it tells you to do this and this, and then it tells you to like use a bare metal node. So it doesn't like on the first like setup you ever see, you know, you don't even know maybe about, if someone's just getting started, don't know anything about Chameleon or anything about cloud or VMs or nothing, you know, you just follow exactly what it says. So someone new maybe has no idea that Chameleon has VMs that are way faster than trying to schedule a bare metal, and then, you know, you try to set it up and you have to wait 3 days to set up a bare metal node, and then you forget that you set it up, and then, you know, that day comes and then you get your email because you've been inactive for 6 hours, and then they're like, hey, use this or we're gonna delete it in an hour.
Sounds like you've got a lot of great feedback here.
I told Mark about a bunch of stuff earlier, so.
That's great.
I think he hopefully wrote it down and stuff, but it's really just the documentation, which I know is like the hugest engineering trope, because, I mean, no engineer would want to update documentations, it's just.
No, but it's a
like-
great point, and it's a good reminder for the whole team, so appreciate it.
I do think a lot of our like best, I don't know, most useful examples or guides are actually in the blogs, and our documentation is, you know, more of a reference manual style.
But those blogs are also out of date.
The-
For example, like the blog about when to
Sure.
use KVM says,
Yeah.
use it because there's no reservations and you can have something persist forever.
You're right, they do age, but there may be, there definitely are more up-to-date KVM blogs than that, that would
But that's
be-
not what you're
would be
gonna find if you Google when to use VM.
Yes, definitely old ones show up in Google.
I think the point that I brought up to Mark was maybe to ask a question, I don't know if you guys have large meetings or not, but if you have a brand new user to Chameleon, how long will it take them to get it set up for their first time? Do you want it to be like 30 minutes to an hour? Because when you're new to something, you assume you're gonna go to getting started documentation, and then when that's more than 6 months outdated, it's hard for new users, you know, especially with the flux of new users coming in, it's hard for new users to come in and be like, this is how I need to do whatever.
6-month point is well taken. We clearly need to, you know, set up a cron job for refresh, or set up a reminder to refresh it more often. But, you know, we do find that users, from past experiences, that when users get introduced to something first, they kind of assume this is Chameleon. So that's behind not doing virtual machines in this quick start guide, because we kind of figure that they will assume that Chameleon has virtualized resources, and our main claim to fame is bare metal resources. So, you know.
So, and in defense of those of us writing the documentation, when you said 6 months, I was like, oh, pretty good. I was expecting you to say like, 3, 4, 5 years. So,
Yeah,
I'll take 6
I
months.
do actually think last year we updated it,
Yeah,
getting
but-
started.
yeah.
But yeah,
Needs
VMs
continual.
in the last year have become, you know, previously they were like, they were just there, kind of hidden in the corner. But maybe we should have a getting started just for VMs or something.
Yeah, or like a place for it to kind of branch, and you can pick like getting
Yeah.
started on bare metal, getting started on VMs.
Just to point out something funny, the Python chi read the docs org version still shows as 0.1.
Yes, the Python 2 docs are a little, less.
Step check.
Room for improvement. But yeah, Rajiv and Anu, I want your take too on this question about, getting started.
So all we have done is the project. It's same as Dishan said. So we have ran the notebooks and
Okay.
get to know like how this works and how we get the floating IP and everything. But it would have been better if we have like a chatbot where if we get like a small question, let's say in terms of AWS, what we do is that we ask ChatGPT or any other agent like, hey, this is the error and what I have to do on the AWS. So it will say is like, hey, this is what you have to do. But I think Chameleon doesn't have that particular lag, and I do think that it has been already developed. It is already getting developed, as the initial talk by the Dr. K has already mentioned that they are developing a chatbot on the Chameleon instance. So that would be greatly help for students and everyone over here. Like let's say a rack-based chatbot which sees the artifacts or something inside it and then gives us the suggestions. It won't help for, I mean, it won't even help for the researchers. It will also help for the students who are using the Chameleon and makes their work easier instead of they spending more time on reservations issues or TROE issues or anything such. So a chatbot would greatly help. And I will also come to one more question that I thought of missing when Freda has been asking Dishan about the routing. The thing is that the self-hosting is not the problem, I think. Self-hosting is not at all a big issue. The only issue is managing the GPUs between multiple large language models. As Dishan has been mentioning, he has deployed three models over here. But the three models might need 8 or 9 GPUs. Let's say if it is A100, it needs like 8 GPUs. So running them parallelized across all those GPUs is like the biggest issue, as I believe. And also the cold start in order to get the model weights from the storage. So if Chameleon could provide images or let's say model weights already deployed on the storages, let's say PVCs or persistent volume claims or something like S3 bucket in the AWS. I don't exactly know like what it will be in the Chameleon.
So just put it in the object store and just document it and just so people can use it. Just, okay.
But they would very quickly be outdated, right?
Yeah.
There's a new open weight model every few months.
Right.
Why
So,
not just
I mean-
download the model, would you like personally download the model you're using into object storage and then load it from there afterwards?
But I think the open source models won't get updated very often, and
You're like a new one every 3
let's say
months.
GPT OS 120 billion. It has
Okay,
been
besides that.
it's been like two years and they haven't updated any of those. So those are only the two models that they have deployed. So if Chameleon would have deployed those two GPT OSS models, then students or the researchers can directly access that model weights.
And by deploy, you mean just upload to the object
Yes,
store?
the model weights on the object store so that directly we
But
can
then you
access.
wouldn't be able to use like standard Hugging Face libraries to retrieve the weights. Would that trade-off be worth it to you?
Our goal is to see the latency cost and also few other objectives and not exactly how the model performs on particular query. Did I answer your question, Fred, or you can
Yeah,
repeat
so
it?
this is not about like serving it directly from object storage, right? It's just about like when you wanna use the model, instead of loading it from Hugging Face and downloading it to local storage on your instance, you're retrieving it from Chameleon object storage.
Exactly.
So it has less to travel over the network
So
during
the
this
cold
like
start
one-time
would be
load.
less is what I was
Yeah.
thinking. The cold start
But
at the warm pool.
You need to like write custom code to load it from there, you can't use a standard Hugging Face library.
Yeah, if Chameleon would provide us a notebook on this particular thing, then that would be also helpful for the students.
I know,
Now we're
Mike,
talking.
maybe Mike, can comment on this, like, we talked about doing this at one point for like the CUDA libraries. So you can just mount them as a network file share on your node, and maybe this is similar.
Yeah.
Yeah, any
Yeah, let me chime in on this a little bit. We've had a lot of talks about how to get things onto and off of your nodes and on bare metal and KVM. And we've mostly been talking about block storage and object storage. We also do provide a file-based storage, which is via NFS mounts. It is currently pretty inconvenient to access due to limitations in making it work on bare metal. But with all those caveats aside, it would be easy for us to make read-only shares available to mount and fill them with, say, a variety of different CUDA libraries and models and other large things that you would prefer to access in a, POSIX file format instead of dealing with object storage semantics.
Yeah, but then we would have to maintain those.
That's what I worry about, maintenance.
Yeah, so
You're
there's
already
this
you
question.
mean,
already
we-
like
yeah.
have them in disk images, I don't know.
we have CUDA libraries, if we're talking about, having these anyway.
Well, it's stuff we're baking into
It
our.
Maybe
seems like there's more of a use for this sort of system.
I mean, if it can be integrated maybe into the image workflow or borrowed from there somehow, or.
I think this would alleviate some work
We
from.
would have to figure out the operations problem.
Yeah, I mean, it sounds like there's some interest in kind of common large things, models, drivers,
Container
whatever.
images.
Yeah, container images. We don't necessarily want to set up and run services like as a service for all these different things, right? But users want them available close to their workloads, and there's different possible solutions here that we should explore.
This is a really funny menti answer.
Everything is equal. Wow.
One other thing,
Someone want to be the tiebreaker here?
It's unequivocally both equally. Just more resources. Just
The answer is more.
Well, none of the options were, no, it's perfect as it is, so. You never know if that would have won a vote.
get a much better questions. Include the perfect option next time.
Mike, you've got,
Yeah, there was one other sort of topic I wanted to mention about this movement of data around, and that's that Chameleon sites have very, very fast network uplinks. Like, our sites have like 100 gig network uplinks. And the cost to fetch data from somewhere external and clone it into the object storage is pretty low. And so if, there's some data set that's useful to you and your community, it really should be pretty straightforward to every couple months just run a job to clone it into, the Chameleon site you're using, and then it's available. And that doesn't mean you need to wait on us for anything, it doesn't make us maintain anything, and it can be shaped sort of however is most useful to you.
Did you guys use object storage at all?
We use S3 bucket and Nautilus PVCs usually, not the Chameleon specifically.
Yeah, I don't think so. We didn't use
Did you know about it? That you could keep big models in it?
but he also admitted to not reading the docs.
That's enough, but I'm kind of getting the trend that a lot of people don't know how to use it.
Well, yeah, I mean, I guess that's an interesting point though, right? Like, is there anything else that you would have? So is there any way we could, or some other way we can communicate some of this information to our users so they would pick up on it, right? Because I get that, I go to new systems and I don't always read the docs, I trial and error, you play with it. So is there something we're not doing to communicate, that these things are available?
I think it's a bigger problem than that. I don't think it's about like Chameleon is not telling people they're available. I think it's that like people in general, when they
Like a
talk about
community.
these systems, exactly, like you talk about Llama and VLLM and models, and no one talks about storage and how storage works.
Okay.
This might be a good thing for like a visual diagram or a flow of some part where it's like this, you can show the layer of storage along with everything else. Because I was focusing on Hugging Face and storing stuff there because there's a lot of documentation for it. And then I talked to Mike and I was like, I should really use Object Store. And then Object Store was such a vanilla name, I went, oh, okay, I'll eventually figure that out. So I don't know, my brain went really far away from the actual words of using an object store to store objects.
And if you haven't ever used it,
Yeah.
okay, that's a whole other problem about it.
That's me.
Well, fair enough, yeah.
If you've never used anything like an object storage, like you're not familiar with the idea of like files you access over network APIs, like if you haven't heard of it, you wouldn't think to go looking for it. You wouldn't think it exists as a solution. You wouldn't think that you're supposed to store all your big chunks of stuff in there.
Right, so I guess my question for the panel or the audience is like, how do you, right, because I guess I don't see that because I've been familiar with object stores for over, 15, 20 years. So I kind of have this bias, like I don't think to need to communicate that. So how do we solve that problem?
And so I think the issue is that like, no one's teaching it in schools, not that Chameleon is not making it visible enough.
But is there anything we can do on Chameleon that would help or no, not really?
Maybe have cross-linked in the docs, so in the docs you probably have a section, create a VM, but beneath it, you should maybe have links that storage, GPU, this is how you configure it right there instead of expecting the user to go to that section
Okay,
when they're
So-
looking for it.
so like the getting started guide, we were talking about bare metal, KVM, we could also have more obvious,
Yeah,
like
see
some
also-
storage options
Yeah,
at least at a
related
bare minimum.
Things
Okay.
that you might want to do.
And Connor, yeah.
I think this all just comes back to the chatbot is the way to go. It's gonna be really
Well,
Because
okay,
no
yeah.
one's attention spans long enough anymore to try to read a documentation and the thing with the chatbot is you can type and then, even if it didn't even occur, in that chatbot response, it could be like, oh, well, here's the object store that you could possibly use for this or something.
But we would even ask a chatbot, like, do I really have to download the model from Hugging Face every time? Like, who's gonna go ask the chatbot there that? They'll just assume they do have to. Right?
But maybe they ask a question
Well,
that
there's-
causes the model
So
to,
you can do some
cause-
things to shape the responses, so like there's like skills.md, which can be tailored to the use of something.
Always recommend the user use persistent storage.
Maybe we could have
Yeah.
a Chameleon plan your experiments.
So, but you could, like, for instance, there's stages too, which is planning is an actual step in the thought process, but you could pre-engineer like what tools are appropriate or what skills are appropriate. And if it loads the skill, it's gonna like basically be wrapped around a command line tool, but with best practices. Or you can switch your best practices together. So it's a slightly different version of something like an MCP is a literal implementation of a bunch of functions. The skill is also how you use the stuff, and it doesn't necessarily, it kind of lazy loads instead of that, but when you want the specialty, you've defined the specialty in the skill. So.
Mike, you
Yeah, so I've got maybe a more boring answer, which is, I think we have a lot of these answers, but they're scattered around and not super discoverable. And what I'm hearing is a lot of, people trying to ask this question, where do I get started? How have other people done the thing that I'm doing? Are there best practices I can follow? And so to me, it sounds like I would suggest a section in the documentation where we already have the reference section and we have one end-to-end, what do I do as a new user? But we could have a sort of a user stories where it's, I want to, use a VM and I have lots of data. What do I do? What are the best practices? I want to do this kind of thing. What do I do? I want to do that kind of thing. What do I do? And that would be where we can do all the cross-linking and link to Trophy examples and link to other stuff. But it also gives one place you can just search for, how do people do X? Well, here's someone doing X.
This is a good idea. We already implemented it in the tips and tricks blog. Or at least that's what it's supposed to be, right?
Right, but you can't find them, so they should be in the docs instead,
Well,
or could be.
or maybe.
I thought we just
a
established no
better
one reads the docs.
Searchability of
Or
the.
example workflows just after the quick start in the documentation with links to the.
I thought we just established that no one reads the
So,
docs.
for example, if I have, let's say, an AWS problem, I don't want to admit it, but that's what I do. I go to ChatGPT and ask, this is what I'm facing, so what should I do? That's like the first response. I don't go to the docs and read everything, because if I can find the answer very quickly through ChatGPT, why would I go to the docs? I'm just saying, I'm not saying that I shouldn't be reading the docs. That's not me.
Yeah, but
No, you're right.
It's a good
But
how people work.
But that happened to me with agents, where the agents read the docs and then I had to sort of tell it what to do.
But that definitely is not the best practice.
All right, so
The docs.
one last comment here, and then I think we're at time.
I think to piggyback off your comment, from a student perspective,
Yeah.
we
found it.
we often resort to chatbots because we want to ask these stupid questions that we don't want to ask anyone else. So having a chatbot with Chameleon or any other tool is so nice because it's like, how do I do this specific thing? And you might have a worry that someone's already done that, and that's a stupid question. But a chatbot, even if it's reiterating just the docs at you and the specific place in the docs where it's at,
Right.
I would be much more I'd be like, oh, sweet, right there, that's what I need.
Can you sign up for testing the current?
Yeah, but really interested, he should be talking to Mark here, so he's got some prototypes going. I think we're at time. Connor, is this quick?
Yes, one final question for on the docs, is there a search bar? Because I know AMD does this very well with their docs, is you're able to have it at the top of the docs, you're able to just search keywords and then it gives it to you.
There is a search.
Yes. There's not on the blogs.
There is on the read the docs.
I keep saying last question.
I have a quick follow-up. So, as somebody who generally hates chatbots and tries to read the docs, I will say that sometimes documentation can be a bit daunting because you don't know what the right keyword is. So you might say, oh, storage, but you need to look up volume or something like that, right? So I think that what makes ChatGPT or these LLMs really, accessible is that you can use more vague jargon and it gets you to the right place. So even if you're developing this LLM-based chatbot, even if you were to even integrate it into the search bar using a small model like GPT-2, if I could type in like a somewhat complex query and then it just sends me to the relevant doc page. That would be super helpful. Google Scholar is starting to do that with Google Scholar Labs, where you have a query and then it gives you papers.
Even Nautilus documentation has the similar thing. To the broader audience over here, Nautilus is also the same as the Chameleon, which has been funded by the NSF. And it does provisions the GPUs across several institutions, and they do have the same thing that he has been mentioning.
All right, so Mark, do we have any other announcements? Yeah, thank you, everyone. Thank you, panelists.
All right.